Welcome back everyone. In this video, our MaxxFan ventilator. Simultaneously the best RV fan you can get and the biggest piece of trash. So this is our main ventilation fan. It's the MaxxFan Deluxe 7500 and it's kind of the de facto standard RV ventilator fan. Very common to see on overland builds all over the place. But like I said, they do have some big flaws. So let's go through those and see if we can rectify some of that. So firstly is the circuit board, the controls that control the fan speed and direction. These are made without any conformal coating, and what happens is the lid, the hood over top of the fan, condenses your breath or other humidity from inside the truck, and then if the outside conditions are colder than inside, it will condense water on that lid and drip right onto the circuit board, and this moisture then can short out electrical connections and cause corrosion on these parts. I did do a video on this in the past, maybe 2 years ago. I'll put a card to it up here. So that's pretty simple to prevent actually. Just get yourself a can of conformal coating and give it a good thick layer of conformal coating over top of these electrical parts, and that will prevent water from causing any corrosion. I have heard of other people actually pulling this board out and relocating it somewhere inside the vehicle and just running extension wires to the fan motor itself. Also an option, but in our case I have put the conformal coating on our circuit. The second problem with this circuit board is it's widely theorized that it fails at voltages over 14 volts. This one has actually succumbed to that death. Fellow camper here donated it to me just for fun. But yeah, apparently if these boards see an input voltage over 14 volts, the processor just dies. And I've tested this board. I can put 12 volts in and there's a regulation circuit and it is still feeding the processor 5 volts, but the processor isn't running. So many people have used step-down converters to step down the voltage in their vehicle to no more than 12 volts to reach the fan. That does cause some problem though, because the fan motor is still going to pull close to 100 watts, and so your step-down converter needs to be able to support that load. The next problem is the DC motor. It's prone to squeaky brushes very quickly. I typically take my motor completely apart every 3 to 5 months and clean up the armature and the brushes, because there's all sorts of crud in there, and then of course it works its way into the bearings and everything gets really squeaky. Unfortunately, for the sake of this video, I just cleaned mine, so the squeaking has gone away, but I'll see if I can dub over an audio clip of some squeaking that I've recorded in the past. So here's my original motor taken apart for demonstration purposes. This is a very common brushed DC motor configuration. For those who don't know, there are 2 bearings, one at each end of the motor, thusly, and the motor spins inside this housing, which contains magnets. To cause the motor to rotate, we use carbon graphite brushes, and they are placed in the motor approximately like this, and those carbon brushes contact these copper sections on the commutator. The segments of this commutator are sectioned into 12 or so positions, and as the motor rotates, the carbon brushes touch a different set of windings and cause the magnetic fields on this armature to pulse in sequence, and then those electromagnetic fields interact with the permanent magnets in the DC motor case, and that's what spins the motor. So this, as I said, was my original motor, and this copper commutator has tarnished somewhat from being out of use for some time, but this trench carved in here should not be. The copper commutator should wear very little, and the carbon graphite brushes are normally considered the wear item or the consumable. But in this case, it's my belief that these brushes are far too hard for the alloy in this copper commutator, and it's trenched its way right through it, and in several positions like here and here, it wore right through the copper to the insulator in the middle. So I've been doing some reading online, obviously, as one does, and it seems to me that motor manufacturers, especially big industrial motor manufacturers, will manufacture the motor originally with a very hard composition for the brushes originally, and that they do that so that it polishes this copper commutator nice and smooth and mirror-like, and then when those brushes are worn, they'll replace the carbon brushes with a softer composition, and that is done so that you don't wear away the copper on your commutator completely away. Rather, you just burn through brushes every year or two or whatever, and put in new brushes, clean it up, and you're good to go again. Now, this motor obviously is pretty far gone. If the motor would stop in this position, it wouldn't start again, and I'd need to take the screen off and spin it by hand to get the motor over these dead spots, and then it would coast past them and flywheel through and tick through, and it would be mostly fine. It was a little noisier, but that's what I needed to do because it was a hot day in Mexico. But I can't get this motor here. In fact, now we even have friends who have flown back home to Canada, and they want to buy a spare motor to have on hand, and they're not available. They can't get this motor from MaxxFan presently. So I'm not sure what the deal is with that. It's a simple enough motor, and there are very, very, very similar motors to this on Alibaba, AliExpress for $10 or $12. They're not such a unique thing, but to find one exactly this size with the mounting position and the same shaft diameter for the fan does make it a lot more difficult to find. In fact, I can't find them. So, since we need to have a spare for Central American travel as we continue south, my plan to rejuvenate this motor and get it going again was to chuck this armature up in the drill and then take a file and file all this copper away, and then I found a plumbing fitting with a very similar outside diameter, and I would file that insulator down until it reached the inside diameter of this fitting, slip that over, take a saw and cut the end off, and then slot each of these slots back, and then solder a connection back to the windings. Now, it took me quite a lot of doing, but I did actually find the original size commutators. These I bought on AliExpress. I'll put a link in the description below, and they are the exact number of commutator positions, same shaft size. It is slightly loose. I don't know if they should be quite that loose. I assumed it would be a tight interference fit, but that's no problem. I can put some Loctite on there to keep it in place. So that is something I'm going to try and do here without unwinding this whole motor. I'm going to try and sneak this old one off and get this new one on here. Alright, when I set out to make this video, I thought it would be a brief overview, kind of showing this motor and how I retrofitted it and gave it a tune-up, and then I'd go straight off the deep end and install a crazy brushless motor. Now, I went to great lengths to get this e-bike motor. It's a 6374 140 kV motor. Puts out 3,500 watts, which makes this 100-watt motor look pretty pathetic. But I selected this motor because it's approximately the same size physically. It shares a common 8mm shaft, so the fan blade would bolt right up, and the bolt patterns or the mounting position is pretty close. It doesn't quite fit, but it would take minimal modifications to the housing to get this motor to slip in there. Unfortunately, those dreams were dashed really quickly once I had it in hand, because brushless motors have what's called cogging. Alright, so you can feel cogging pretty distinctly, but I don't know that I'll be able to show it. But basically what happens is you see these steps. As I turn it, it jumps from one armature position to the next. Now, while this isn't a perfect example, it'll illustrate my point. This is the brushed motor's armature, and basically the big magnets inside this brushless motor, which I'll use these as a stand-in replacement, what's happening is as it jumps from one armature position to the next, the magnets are so strong that when it gets to the next position, it really snaps over there with a good amount of power. So this isn't a perfect example, but it makes my point. Now, I was expecting this to some extent. I've used brushless motors in the past, nothing new to me, but the amount of cogging on this very powerful motor really surprised me. Now, I was hoping that the fan, which is a 12-inch fan blade on there, would have enough inertia that it would have a flywheel effect and kind of mush through all these steps and you wouldn't really notice it. So as I spin this in my hand, my soft, fleshy hands are dampening the sound. So I've moved my microphone to the tabletop, and when I put the table in contact with the edge of this motor's housing, and that's just spinning it by hand, you can imagine when I spool this up to 2000 RPM what it's going to sound like. And if you can't imagine that, let's connect it to the ceiling and have a listen. Alright, so I've got the motor mounted up there. It's kind of off-center because only one bolt hole lines up, and I'm not going to bother drilling all the rest of the bolt holes. But from there, of course, is the ESC and the old laptop controlling it over serial just for testing purposes. Let me show you what this would have sounded like. I'm going to sweep the RPM from 0 to 2000, and I'm taking my mic off, and I'm going to hold it about at head height, where our head would be if we were sleeping here. Just for context, this is me at a normal speaking volume. Some of these RPMs really get obnoxious because it hits its resonant frequency with our roof surface. Like there. Now you could argue that this is the electronic switching frequency of the speed controller PWMing the motor, but as I will demonstrate now, that is not the case. I've lowered the switching frequency to 10 kilohertz, and I'll demo that now. Again, this is not amplified. This is me speaking at a normal volume, about equidistant to the fan. So clearly this is not going to work. Dreams dashed. Let's get to fixing the old brushless motor. Now there are of course smaller brushless motors that are more suited to the task. Part of the reason this one makes this cogging sound so audible is it's crazy overkill. It's over-spec'd for the job by far. But I selected it, as I said, because it's approximately the same size, so mounting in this housing would be turnkey, basically bolt up, and the shaft diameter was correct for this fan blade. So I could, of course, get a smaller motor, because there's a comparable motor that does comparable work is usually a lot smaller if it's brushless. So this is a spare drone motor I have. You know, it might almost be enough, but then mounting such a small motor with a small tiny shaft would be a much bigger challenge, especially at my kitchen table on the side of the road in Mexico. So if you know what I've done wrong, if I can somehow defeat this cogging effect in software somehow, or know what I'm doing wrong, feel free to let me know. I'm happy to be wrong once in a while. So the first thing is the hardest, I guess, and that is getting this original copper commutator out of there and replacing it with this one. Now, as I said before, the way these are manufactured originally is this commutator is in place, and then there's a winding machine that winds these windings onto the stator, and they're hooked around these hooks as it's wound, and then they pinch it closed, and that crushes into the copper wire. So the correct way to do this would be to unwind all this copper, put on the new one, and wind new copper in place. But I'm going to try and cheat and unhook these, breaking off the original hooks, and then somehow snake this in there. So as I do this, I'm finding easier ways of doing it. Just getting under this hook with the cutter and then lifting it. And then I can wiggle the wire up out of the way a little bit, and then just cut the whole hook right off. Alright, so I've got all these little hooks cut off. Some of them have taken out, and pulled this circlip off the end. And now let's just wiggle that out of there. It's not as tight as I thought it would be, so this one being kind of loose isn't so unexpected, and it's actually tightening up the closer I get, so that's promising. So, as I suspected, if I was to push this on here now, these wires are just too tight to be able to hook them over these hooks. And in fact, the new commutators, the hooks are much beefier than the original. So what I'm going to do to get around this problem is cut all the hooks off and file it smooth, and then I'll come in here and just solder the wires to the end of the commutator positions. Alright, got these hooks all cleaned up and out of the way, and I'm just pre-tinning a little bit of solder on each of these points. So that when I get in there with the motor windings, it's a little easier to get in. And I'm just going to solder these a little bit just to clean off some of the enamel before I get in there for real. Alright, so I've got it kind of lined up here. The timing obviously is going to be very important, much like the timing of a combustion engine. These segments on the commutator determine when the next electromagnetic coil is fired, and thus the speed that it runs. And if I get this out of time by just a little bit, it'll run faster in one direction than the other direction, which isn't the end of the world, but this is a reversible fan, so I would like it even if possible. But to the best of my measuring ability, before I took the old one off, these slots in the commutator lined up to the middle of these iron stator sections. So I've eyeballed that as close as I can, and now I'll just press it in using my kitchen table pressy 1000. That's not quite there yet, but I'll go outside and wail on it and get that pressed on. Alright, so I got that pressed on. Actually did it by hand without too much problem, and now I just need to solder each of these windings to the end of the commutator. Alrighty, got it all soldered up. I started cleaning it up a little bit, but I thought I should show you before and after, so that you didn't think it looked beautiful. The solder did get a little bit globulous, but I should be able to file that down Additionally, that area where the solder is doesn't come in contact with the brushes. As you can see here on the original, they're mostly over here on the right side. Did a little bit of filing, and I thought I'd just show you my plan for smoothing this out. I've just chucked her up here in the drill. I'm not going to go crazy, because this likely is nowhere near concentric. But I'll just give it a little tickle until I'm through all these solder spills that have spilled onto the copper, and then I'll polish it up the best I can with some higher grades of sandpaper. Alright, as you can see, I've got the copper commutator cleaned up again, cleaned up that solder that's spilt over onto the face. And now I'll polish it up just a little bit more with some fine sandpaper. So I've just got a piece of this foam sanding block, and I just cut off a strip of it, soaked it in a little bit of water. So that's as far as I'm going to take it for now. I may polish it out later, but for now this is good enough. And the way to test that it's working electrically, of course, is to take your voltmeter, set it to ohms, and then just measure 180 degrees across as if you're using chopsticks. And as you can see on the meter, this set is 1.45 ohms, the next 1.45, 1.45, 1.45, 43, 44, 45. You could really do this to infinity, but once you go around once and they're all connected, then you know it's good. Let's put this back together and I'll show you a few more upgrades as we go along. Alright, so there it is. A new commutator all soldered on. Tests like it should work good. I've cleaned everything up with electrical contact cleaner, the housings and the inside of the motor housing where the magnets are. In fact, this armature just rained out mud. There was lots of carbon buildup inside the windings themselves. And I just noticed the red color in this buildup here at the bottom. Hopefully that's coming through on camera for you guys. But that's all the copper that got chewed off of the commutator since the last time I cleaned this, no less. So some of this is the carbon too, but lots of copper in there. But assuming you've just taken your motor all to pieces just to clean out the carbon in the first place, now you need to put it together. So let's walk through that together. One thing I wanted to mention is I will be replacing the original 209Z ball bearings. They sound like this with these Bones precision bearings, which I can't hear at all. So I've got those, and they sit inside these little rubber booties, and that just acts as a little bit of a spacer, which allows them to make castings with poorer tolerances and still have the bearings fit. So one bearing goes in the back. These should be oiled. I'm not going to oil this because I'm going to be taking this apart shortly. I'd like to find some different brushes, which I don't have at the time of shooting this video, so I'm putting it back together with the original brushes, but I don't want to leave those in there. So for that reason, This motor is not going together permanently quite yet, so I'm not oiling the bearings, just so I don't have to deal with an oily mess. So once you've got your bearing in there, you can get your brush card, and this little rubber doodad lines up with a larger gap in the housing here, and the alignment pins fit just like that, and then this little brass clip holds on this little white part. So place it on there like that, and the screw. If you don't have the right screwdriver, feel free to use the wrong one. Or if you do have it, you're just too lazy to go get it. The same applies. So there's the brush card all in place. Now, of course, these brushes are spring-loaded, so these small brushes fit in here. Some versions of the motor have like a boomerang-shaped brush that connects to this pin, but these ones are just straight brushes. Sorry, straight springs. So the trick is you got to pull this back and get all these springs in place, and then close it up really fast before the springs pop out of place. And so the trick to doing that with this motor, this design of motor, is to place your brushes in line like this, then get your motor armature and slip it into the bearing, and then pull the brushes back just enough so you can slide it down like this. Man, that sounds like a bag of nails. The brushes are going to sound like crap until they wear in, but let's hope it gets better quick. Then, once you have the motor in this state, you can take the can, line up the slot for the wire, and it's going to want to jump to the stator like this, to the armature. So just be aware of that, and of course it will snap over and hit the magnets. Das is okay. Then you need this fancy little shim, thrust bearing, thrust washer, and then press your front bearing into the housing, and be sure you have your rubber grommet on there. And then there's a little crush section on the can here, which lines up with this notch here. Ta-da! And that's it, mostly together. And then the screws thread straight through the whole thing, which becomes a little bit of a challenge because they want to stick to the magnets, but very doable. And the other side. Don't need to go crazy on this. And there we have it. Those brushes are really making a racket right now because they're not well meshed or well paired to the commutator. But let me show you the trick to wearing the brushes in. Alright, so when this motor was removed, I at the time didn't think that I'd be rebuilding it, so I just lobbed the wires off. But that's no problem, because now I will put a connector on here, again just temporarily, but this will be nice for future motor changes because it'll have a connector handy and I don't need to take the whole controller apart to wire in the new motor. I'll just connect it there. Alright, so here's a little trick to breaking in your brushes. These brushes are used, but it would apply just the same if you replaced your brushes. And this trick comes from ye olde days of radio-controlled airplanes. What you need is to run the motor very slow, and a very easy way to do that is to reduce the voltage, and for that I'm using my variable power supply, and we'll set it at 1 volt and just let it turn slowly for a long time. I don't have a long time to make this video, so set it at 5 volts there, 4.3, and you get the idea. I would let it sit and run like this for 8 or 10 hours with no load on it, just, and I'd probably slow it down actually, something like this. So that's a trick from olden radio controlled car and airplane days. We'd actually submerge these in either water or antifreeze just to carry away the particles of carbon as they started to break in. But in this case the motor's sort of sealed, unlike RC motors are usually open canned, or oftentimes they were open canned. So anyway, this is how you'd break in a motor if you've got some low voltage battery, radio controlled car battery or something like that. You can get away with 5 volts. If you don't have anything, if you don't have a way to do this whole power supply was $40. Fun thing to have on hand, but running it at 12 volts with no load, it's only pulling 200 milliamps right now. That wouldn't be the worst. You could certainly do it under no load conditions. Probably would only take an hour or two, and then have a look at the brushes, clean out the carbon dust, and it should be ready to install. Alright, so there it is. I'm going to let this run for many hours, just slowly wearing those brushes in to match the new commutator, and then I'll check how it's doing. I would like to find new softer brushes, as I mentioned, but there's the little corner stores at the side of the road on Mexico Avenue don't have them in stock. Surprise, surprise. So I'm going to let this hum away, and then it'll be ready to swap in if this motor starts giving me any problems. I did just rebuild this motor, so it's doing fine right now, but when it starts squeaking and annoying me, then I'll have a motor to swap in. And with a quick connector on there, I'll just be able to swap it real quick. So that's great. And if we run into someone on the road who's got a terrible squeaky motor, we can swap it in for them too, and then rebuild theirs. I'd like to thank all of our supporting channel members, whose names you see here. It's their ongoing support and lovely, lovely comments in the members section that encourage us to keep going and making these sorts of videos, which are sometimes more painful to make than just doing the work would have been, but we enjoy making these videos for you anyway. So thanks so much to the members. Appreciate it very much. Check out the members only video playlist, which I've linked in the description. If those are the sorts of videos you're interested in seeing, consider hitting the join button down below. And yeah, thanks so much for watching. We'll see you next time. And for today's extra content, a quick hack for you. Oftentimes our screen will get sucked up into the motor and start making this sound in the middle of the night, especially if the screen is covered in goobers and buildup and the fan is sucking outward. It'll pull the fan screen up into the motor like this. So let me show you a quick hack for that. But regardless, just get a little magnet and stick it right on the tip of the motor shaft like that. And then on the screen I've attached one magnet on each side so they're attracting to each other. And just to the upper right of that magnet, you can see kind of the rub mark where it's rubbed through. Adjust that to about the center of the rub mark. And then when you put it all back together, those magnets are opposing the magnet on the motor shaft, and it won't rub anymore. Bye.